Thank you very much, Andy. I have a small but illustrious audience. So I'm going to tell you about a series of papers over the last 40 years, only the latest of which was by me from last month. What I'm actually going to do in this talk is write down a very detailed specific model. There's going to be a Lagrangian. The model will consist of a bunch of fermions that all go in one direction in 1+1 dimensions, and then there's a little impurity degree of freedom at the origin that does weird things to them. And so most of what I'm going to be telling you about is that particular model. But I thought I'd spend the first 15, maybe 20 minutes just motivating where that model comes from, why it's interesting, and in particular what it has to do with the standard model of particle physics, which is where it really has its origin. So there is a very old story that I have been obsessed with for maybe 4 or 5 years now, that was first discovered by Callan in the 1980s. And the story is the following. You go out there somewhere in the universe and you find the magnetic monopole that exists somewhere. And you put it in a lab and you start throwing things at it, because that's what we do in particle physics. So you throw, for example, an electron at the magnetic monopole and you ask what bounces back. And the astonishing answer to that question is nobody knows. This is a puzzle in quantum field theory that after 40 years, maybe more than 40 years, no one has figured out the answer to, which I find very surprising. So the deal is the following. You should throw the electron at suitably high speeds. The electron should be at an energy of bigger than, say, 100 GeV. At those energies, the Higgs is essentially irrelevant. Said a different way, if you just turn the Higgs off, you can do this at arbitrarily low energies. And the point about those energy scales is the standard model is a chiral gauge theory. The left-handed fermions and the right-handed fermions experience different forces. And what the monopole does is its presence kind of exacerbates the fact of that chirality. And in a way that I will describe on the board in a little more detail, what you find is that the ingoing scattering states in the presence of a monopole carry different quantum numbers from the outgoing states, because of the chirality of the gauge theory. So somehow the 4D chirality turns into a 2D chirality in the context of scattering off a monopole.
So what's QED?
QED is completely trivial.
Exactly.
Yeah.
So all the modifications are due to one term.
They're due to the fact that the standard model can only be written in terms of Weyl fermions, not Dirac fermions. I'll clarify this a bit more detail. All right, so this was first pointed out by Callan. Callan pointed out the following, that if you throw an electron at the standard model and ask, at a monopole, and ask what bounces back, naively, the equations tell you that what bounces back is half an electron and half an antiproton, which doesn't make any sense at all. What do those factors of a half mean? So in some sense, the purpose of this talk is to tell you what those factors of a half mean. All right. The key idea is simply that monopole fermion scattering is weird, and there's a lot that we still don't understand about it. Let me just tell you a little bit more about how this works in detail when you actually set up the scattering problem in a context of a monopole. So what I'm going to do is look at a simple warm-up example. And the way the logic of this is going to work is the following. I'm going to write down a theory which doesn't make any sense. It's going to be a theory that has a gauge anomaly. It's a sick theory. And all I'm going to do is just set up a thought experiment that is a manifestation of that sickness. So we'll see from doing an experiment why the theory doesn't make any sense. And the theory is the simplest such theory. It's D equals 3 plus 1. And it's a U1 gauge theory coupled to a single charged Weyl fermion. If this was a Dirac fermion, this would be massless QED. Nothing wrong with massless QED, but it's a Weyl fermion, and so it has a gauge anomaly, and the theory is just sick. It's not a theory we should really consider. As I said, I'll just cook up a situation where you can see the sickness. And so the situation is the following. What we're going to do is put a magnetic monopole here. It's just the north pole. It's going to be a Dirac monopole. And I'm going to just look at scattering states of this Weyl fermion off this monopole. Okay? So it's a rather well-known calculation. If this was some electrically charged defect, what you would do is split these the solutions of the of the Weyl equation into spherical harmonics, but those spherical harmonics get distorted a little bit in the presence of a magnetic field. They're called monopole harmonics, maybe? They should be called monopole harmonics. They were written down by Yang in the 1970s, so it's a very well-known story. What you can do is the following. Of course, they split into angular momentum modes. There's acute subtlety because fermion obviously has angular momentum a half. But in the presence of a monopole, there's an extra shift by a factor of a half that Poincaré first discovered in 1897 or something. So even though this has spin a half, in the presence of a monopole, the angular momentum modes are integer valued. And what you find is the following. There is obviously a whole series of angular momentum modes. This is j equals 2, this is j equals 1, this is j equals 0. And the key to this paradox is the fact that the lowest angular momentum mode, the S wave, is chiral. The lowest angular momentum mode is either ingoing or it's outgoing, but you do not get both. You just get one. Whether it's ingoing or outgoing depends on the sign of the charge of the fermion times the charge of the monopole, the sign of E times G. Okay. All the higher angular momentum modes, they're completely obvious. They have ingoing and outgoing modes. There's also an angular momentum barrier. So because of the angular momentum barrier, they don't actually know about or get to the core of the monopole. They come in before they reach the core of the monopole. They turn around and they go back out again. Your question, what if you had QED with a Dirac fermion? Well, all of these are doubled, including this one, but the double goes the other way. So QED, there's no problem at all. If you have Dirac-like, vector-like fermions, it's this spin polarization which turns into a chirality of the S wave in the presence of a monopole.
So the other ones have the same degeneracy as if it was not chiral?
No, if it was Dirac, these would double as well. You'll get two these this way and two that way. Yeah, everything doubles with Dirac. By the way, this spin polarization of the lowest mode is very familiar in other contexts. If you look at graphene, for example, in a magnetic field, lowest Landau level has half the degrees of freedom than the higher Landau levels because it's spin polarized. It's exactly the same physics that's responsible for this. That's exactly where we're going. Yes. Yes. All right. Other questions? Okay, so you can now ask, what happens if you throw an S-wave fermion into this? What comes back? The answer is nothing can come back. There's nothing in the S-wave that can bounce out. That's okay, because this is a sick theory. And so all I've done here is just cook up a physical example where you can see a paradox in the physics, that if you throw this in, nothing can come out. It's a manifestation of the fact this theory does not make any sense. Okay. Andy. In the Dirac case, and we'll get there, this doesn't experience an angular momentum barrier, even in the Dirac case. Hits the core of the monopole. The monopole is a singularity, so you have to impose boundary conditions. So you have a choice as to what comes out. Depends what boundary conditions you impose. Actually, the U1 gauge symmetry means the only choice you really have is a phase shift, which is actually the same as a theta angle, essentially, in the theory. But yeah.
Steve would basically say that monopole is a black hole.
No, so you might just think this just piles up there. That's not really possible. Yeah. It's the simplest way to explain it. It would be like this would then have a continuum of states. This is a massless theory. And so these things coming in carry electric charge. So it will turn this into a dion. But the thing coming in can have arbitrarily long wavelength and arbitrarily low energy, even though it carries electric charge. So if it all just piled up, what you'll be able to have is a dion that can carry electric charge at arbitrarily low cost of energy. It doesn't really make sense. And in fact, it's not what happens.
So you're thinking about the monopole as a very heavy object, singularity. You're solving the Dirac equation, quantizing the Dirac equation in that fashion.
In the presence of a Dirac monopole, yeah.
But if it was lighter, and some people start trying to play with adding interactions between electric charges and magnetic charges, treating that as a particle,
center of mass motion, this is still the right. In the center of mass frame, this is still the right description. It's not going to help you.
Yes. But some people ask whether there should be extra terms in the action corresponding to an extra interaction.
Oh, I see, but that leads you into all sorts of difficulties if you want to keep Lorentz invariance, and I've not.
In writing it down, but there's a lot of people who say that's what we need to do.
I think starting with Svansiger, as we'll see, this is not the resolution to this. John Turning and Chabachaki have been sort of playing with these ideas, some old ideas of Svansiger in this context. I'm being recorded. They're very interesting papers. Oh, yeah. There's an interesting story. I don't think it's the right resolution to this. All right, other questions? All right. So this is what happens if you had if you have a sick theory. What happens if you just have a theory with? Let's stick with this. With a whole bunch of fermions, chiral but non-anomalous. Okay, so if you replace Weil with Dirac, there's no problem. Everything gets doubled, ingoing and outgoing. But let's replace, cancel the gauge anomaly in a more interesting way. Let's have still have Weil fermions, but in such a way that the gauge anomalies cancel. So what happens? Well, the higher angular momentum modes just aren't really of any concern. They're there, but we understand what the scattering is. All the interesting physics is in the lowest angular momentum mode. And so what you find is that there's a bunch of ingoing modes that have certain charges related to the charges of these Weil fermions. And there's a bunch of outgoing modes that have certain charges, but the ingoing modes and the outgoing modes carry different charges. If the gauge anomalies in 4 dimensions cancel, you can show that that implies the cancellation of anomalies in a 2-dimensional sense, and in particular the number of left movers is equal to the number of right movers, so there's as many things going in as there are coming out. And moreover, you can show that the sum of the charges squares, which is the 2-dimensional anomaly requirement, is also satisfied. All right, so now you have a problem that potentially could have a solution. You throw in one of these are what you've got coming out, and so the goal is to try and patch up these charges with these charges. Okay, and there's 2 different stories that we can tell here, and I'm going to go through both of them, depending on whether the monopole we have is a Dirac monopole, singular object, or whether it's a Toft-Polyakov monopole. That is a soliton in some non-abelian gauge group in which this is embedded. So if it's a Dirac monopole, then, as I mentioned already, that this is a singularity. You're obliged to impose some boundary conditions on all the fields at the presence of the singularity. In other words, what we have is some boundary condition problem where we have to impose boundary conditions on these fields to map them into these fields. And as Paul said, it's effectively become a 1+1 dimensional problem because we're just looking at lowest angular momentum. So in this case, we're looking for boundary conditions. And if it's a Toft-Polyakov monopole, well, now it's just a soliton. Everything is nice and smooth. There's no singularities. But the problem becomes one of understanding the dynamics. And so what I'm going to do is briefly give you an overview of some of the results that have happened over the last 2 years with boundary conditions, but then I'm mostly going to focus on this second case, looking at some dynamics.
There's no charge conservation.
There's absolutely charge conservation.
So why is there no extra condition?
Sorry. So these are the conditions on the charges of the theory, of the charges of the fields in the theory. But if I throw in, say, a charge Q1, what has to come out has to be a combination of these that carries charge 1. So there's charge conservation in the dynamics. Yeah, but this is the anomaly cancellation condition for the theory to make sense. Good.
So a single electron will not be able to scatter because the charge will. It's only if you have many of them.
No, even if any one of these, you have to cook up. We'll see. I'll give you some specific examples. We'll see. But yes, every single one of these, you should find consistent scattering. Something should be able to come out. Anything you throw in has to come out in some way. That's the question, what comes out. Other questions? All right, let me start by telling you about some boundary conditions. And I'm going to cheat a little bit. It turns out that even the simplest example involving a monopole is reasonably complicated. And so what I'm going to do is give you a much simpler still example that doesn't descend from a monopole, but nonetheless captures all of the physics that we care about. Okay, so this is a very simple example that is in the spirit of the problems you get when doing monopole scattering, but not exactly one of those problems. So a very simple example. And the example is the following. So we've got d equals 1 plus 1 free fermions. We went from 3 plus 1 to 1 plus 1 because we were focusing only on the S wave, only on the lowest angular momentum mode. And the simple example I have in mind is there's 2 fermions going this way with charges 3 and 4, and 2 fermions going this way with charges 5 and 0. Pretty well studied recently in the literature. It's usually just called the 3-4-5-0 model for obvious reasons. And then you want to find a boundary condition on these fields that you put here. So this is playing the role of the monopole. And your goal is to find a boundary condition that preserves this U1 symmetry. Okay. And your first thought is there's no way this is possible, because I've only got 3 and 4 going that way and charges 5 and 0 going that way, and I want to put a boundary condition, and you can just ask, what happens if I throw in a 3? Well, there's nothing that can bounce back that can preserve this symmetry. So it looks like it's not possible. Indeed, if the boundary conditions you look at are Dirichlet or Neumann or mixed boundary conditions or any boundary conditions on the free fermion fields, it's not possible. But in the 1980s, John Cardy taught us that the kind of boundary conditions that you can put on quantum field theories are much greater than just the Dirichlet and Neumann boundary conditions you put on free fields. So there is a whole class of what Cardy called boundary states, Cardy states, that you can put on conformal field theories in 1 plus 1 dimensions, and among that class it is trivial to find a boundary condition that preserves this U1 symmetry. Just exist. You can just write them down explicitly, solve everything about it. So
does the fact that it's gauge symmetry matter here?
No, actually by this point it's going to be a global symmetry. The gauge symmetry kind of lives in 3 plus 1 dimensions, and it means that it's suitably weak enough that it's not doing anything. That's right. Turns into global. You can couple it later, but it's but yeah. At this point, it's a global symmetry. Thank you. It's important. So this is going to be a global U1 in this case. All right. So there exists a Cardy state. Preserving this U1 symmetry. These have been discussed a lot in the literature. I think the first time this appears is in work of Matthias Gabadil and Andreas Recknagel, thinking about D-branes. Ilke wrote a very important paper with Kostas. Do you know this state is in your paper, Ilke? The requirement is that the current associated to this U1 is 0 evaluated there, so no current goes through the boundary. But it's otherwise this is enough to specify the state. It is in your paper. I'm also not sure which one it is. But part of the problem with these Cardy states is everyone has this different view on them. And so I wrote 3 papers with my student Philip Boyle-Smith studying this. A lot of what we did is in your work, and a lot of what we did is in work of Xingse Ru and, of course, of Mateus. Nonetheless, we were emphasizing that these states are weird because they preserve these symmetries. All right, so you can write down a boundary condition, and you can compute everything in this model. And then there's a very natural question, which is the one that I set up to begin with, which is, let me take a charge 3 particle and throw it. And the question is, what bounces back? Okay, it's the single most obvious question you can ask. Of all of these papers, I don't think anyone asked this question, even though it's the thing that's jumping up and down to be asked. Philip and I asked it in our papers, but we weren't smart enough to give the answer. So what's the deal? This way you've got charges 3 and 4. This way you've got charges 5 and 0. You throw in a charge 3, and you ask what bounces back. The charge can't stick on the boundary, which was sort of Frank's suggestion. You can show that the conformal boundary conditions do not allow that to happen. And yet going this way, there's only charges 5 and 0. So what possibly can bounce back? Who has the answer? Yes? They still all have charge 0, though. None of them have charge 3. I'm glad it's not obvious to everyone. If you read the paper, it's cheating.
5 times charge 3.
Then it's obvious. Then you get 3, because 5 times 3 is 3 times 5. That's an important fact. What bounces back? And so the answer to this was given in a paper I wrote with Marika van Beest, Philip Boyle-Smith, Diego Del Mastro, who was here for our school, Zohar Komagodsky, who was also here for the school, me. This is a couple of years ago. The answer is embarrassingly simple. You've got a charge 3 which goes in, and it can't stick on the boundary, and the boundary condition preserves charge, so what bounces back is a charge 3. What else can it possibly be? That's what it means to conserve charge. Trouble is, you don't have a charge 3 in the spectrum. So what's going on here? What's going on, and Andy hinted at it, is that when you quantize a theory in the presence of a boundary or in the presence of a monopole, the perturbative Fock space that you build is not the only thing that can exist in the theory. Okay, it's quite a dramatic statement. It was a big surprise to me. What happens here is that the boundary acts as a portal into a twisted sector of the Fock space. And that what really bounces back is an object which, at least in an abstract sense, is described by the fermions together with a twist operator in the theory. A twist operator which in this case turns out to be a Z5 twist for what it's worth. And so there's a sense in which this object here is attached by some branch cut or topological line. Doesn't carry any energies, very hard to detect, but nonetheless this object coming out lives in a different sector of the theory from the normal sector. So I think it's for me it was a very surprising result.
Sorry, so that's not that. There is actually a charge 3 particle that comes out in that sector.
Yeah. I can tell you the physics. Suppose you do an experiment on this system, and it's just free fermions, but you can turn on any kinds of background chemical potentials or couplings, or as long as they preserve this 3-4-5-0 symmetry. And so with all those experiments, you can convince yourself that this way there are particles only carrying charges 3 and 4. This way there are particles only carrying charges 5 and 0. Moreover, you can compute the central charge. Central charge is just the heat capacity. So you know that there aren't more fields in the game. These are the only fields there are. And then you do an experiment, which is very simple, but something new, which is you make a charge 3 and you just throw it that way and you wait. If you wait long enough, you find something you've never seen in any other experiment, which is a charge 3 particle moving in the wrong direction, which you can still interact with. You can still build puddles of chemical potential and excite it. It's one space dimensions, not two. In some sense, it needs the boundary, but the boundary can be arbitrarily far away.
So what it's saying is, here's my interpretation.
Please.
That I think makes it sound a little bit less fun. Maybe a little bit.
I'd be happy with that.
Confusing. Yeah, the point is, if you've got a boundary and you want to preserve Hewitt symmetry, you have to pick boundary conditions.
Yes.
To preserve Hewitt symmetry. So a way of framing your result is, well, so fine, the bulk theory, you admit that, admit this. But the point is, you can't make a boundary condition that both preserves the U1 and only has these particles. So you're saying there is a consistent boundary condition, some Cartesian state. But then, as a result of that, you have to introduce, there's a sector in which these other problems,
This is exactly right. The novelty is that additional sector does not change the heat capacity. Doesn't change the heat capacity. Doesn't change the central charge. Shouldn't be viewed as new degrees of freedom. You're not just adding extra fields into the theory. That's the novelty. But yes, it forces this.
These other things to exist, which of course you could observe 1,000,000 miles away.
Yeah.
As you say, the string has no energy. So then it's saying that if you run this experiment, you have to do this in this other sector that may still include the 5s, but
That's right.
put another boundary over there.
That's right. But I don't think it makes it any less surprising, because it's still true that all the experiments we do here locally are not enough to tell us all the excitations that can exist in our world.
Yeah. Okay, but sorry to ask again, but I would say that actually there is a particle with charge 3 that is the left mover, but it has to come in place.
No.
So it's not an elementary particle because it cannot live in anomaly. It has to be like
No pair.
no, because if it's connected to the boundary, I would be able to.
But it's connected through nothing you can really detect here. In Euclidean space, there's a branch cut, but in some sense, it's a little bit like spin charge separation or something in height. It's not dissimilar to that. I agree with that. Yeah. Yeah, please.
Space of boundary operators for the monopoles. You have the fractional operators there.
No. We don't really have it. There's not really a boundary operator for the monopole. The monopole becomes a boundary condition. Yeah. That's right, but I don't.
Can I think about these fractional particles as boundary operators for the degrees of freedom which are fractional particles?
No, I don't think so. I don't think so. It's a simple boundary condition. Has an Affleck-Ludwig central charge. In this case, it turns out to be the square root of 5 is the G. But I don't think, it's not, if I throw in this guy and it bounces off, it's not like it leaves behind a memory on the.
I mean, it's a boundary condition changing operator, so it does leave. You say that's.
You mean when?
Square root of 5. Yeah, there. So I agree. The string is.
But this can be anywhere, of course. And
No, it can be anywhere.
it's a topological.
It's right, but it's a boundary condition changing operator at some point in time. So in this experiment, you're saying, obviously.
Okay, so
Yeah.
Pop-
So because G's not zero. The G is experimental measurable thing, isn't it?
That's right. Yeah, absolutely.
It's boundary specific E.
That's right.
So by slamming this in, you change.
I would say differently. I would say that this state with 1 Q equal to 3, this only has support on a Hilbert space with these boundaries.
I agree with that, of course. Yeah, you need the boundary. But that was a little bit different. So you're saying that I should think about putting a boundary operator there?
That's what that is there. In the experiment, so what would happen in the experiment? No boundary condition changing operator hits, bounces back as this funny 3 with the tail, but then we've changed the boundary conditions on this thing. That would be detectable via the G of this thing.
Wait, I've not changed G. G, whether or not this ends, G is the square root of 5. That's a statement about the Cardi state. The Cardi state hasn't changed. So it wasn't like G was 0 here and has jumped here. G is constant everywhere.
Well, that's what. Yeah. Okay. Well, that's the question. Okay. That's to me that's the confusing part. Is what does it leave anything detectable behind with the string?
Let me do the following. Let me do Frank's observation that 5 times 3 is 3 times 5.
Yeah.
So what I do is I send in a whole bunch of q equals 3s. One after the other. It can leave arbitrarily long time between them. What comes out is something which is a whole bunch of q equals 3s. Not 3 5s. It's not in the twisted sector. The branch cuts are between these objects. So now this is something which is not in the twisted sector. If you bring them closer and closer together, this state merges indistinguishably to the state that's 3 times 5, rather than 5 times 3. Nonetheless, these charge, they don't come in pairs in some sense. They come in bunches of 5s in this case. But these charge 3 objects can exist independently in the world, and now I can do it even removing the boundary.
Would also be supported on a different sector of your Hilbert space.
No. No, this is in the...
You would choose different boundary conditions, I guess, such that 3 5 cubic to 5 particles come out.
This is on the same sector of the Hilbert space. There's no twist asymptotically in the Hilbert space. It's all in the middle now.
If you would have chosen your boundary conditions differently, probably it should be possible to get 3 cubic to 5 particles out.
No. Because all I've got to throw in are charge 3s. I throw in one charge 3. I can wait, I cannot wait.
Again, if you have 5 cubic to 3, this lives in a different Hilbert space.
3 times 5 is 5 times 3. They live in the same Hilbert space.
It's not allowed if you have
No, this,
I mean, the point is you have 5 of them, you're back in the original 5.
Yeah,
things,
it's
you're
true.
back in the
but
original.
it's still, yeah. Given this requirement, there's a unique boundary condition you can put on, a unique theory with a boundary. Independent of the states you then build up within there. All right, well, see, people are, I don't know if I've confused people, but I like to think people are just confused because the problem is confusing. I'm gonna cook up a situation where things are much more straightforward, everything is very much in your face, and we can understand better what's happening. Yeah. This 3450 does not descend from a 4-dimensional monopole problem, but all the monopole problems we have become problems of that type. So this was just a simple model that I cooked up to give you an essence of the issue. No, because a proton doesn't have the chiral problem of incoming and outgoing carrying different quantum numbers. So the monopole, its role was only to give you that information. Ingoing and outgoing have different quantum numbers. Yeah, but then it's much more trivial because the ingoing states and outgoing states also have the same charges. Yeah, exactly. Yes, that chiral S-wave mode is the problem. Yeah.
So the line that's twisting where the Cardi state lives, is it the U1 line, topological line?
It's a topological line, but for an additional discrete symmetry, and in each case you have to figure out what it is. Here it turns out to be a Z5 symmetry, for what it's worth. Yeah. Yes. This is just for the Dirac monopole, and now we will do Toft-Polyakov. All right. So after Callan first suggested or pointed out this problem, which was in the early 80s, lots of very impressive physicists have worked on it. Joe Polchinski wrote a paper, Ashok Sen wrote a paper, Juan Maldacena wrote a paper. many more. In each case, I think they're their least cited papers that they've ever written. Joe's had like 8 citations when I first read it, maybe 5 years ago. It's got a few more now. So Joe, in particular, wrote down a beautiful toy model that captures what's going on, but for the Toft-Polyakov rather than the Dirac monopole. So it's just going to be a Lagrangian, and you've got to solve some dynamics. And so let me write down Joe's very simple model. It's in 2 dimensions because, again, we're reducing to just the S wave. And what I'm going to do is write it down and then show you why it captures the spirit of the monopole and then tell you how it's exactly related to the monopole. So what it is a bunch of purely right-moving fermions in 1+1 dimensions. It's n right-moving fermions coupled to an impurity degree of freedom that lives at the origin. And so psi are the right-moving fermions. They're right movers because there's this d plus derivative here. Alpha is a dynamical degree of freedom that depends only on time. And this function here that I've called f prime is a regularized delta function. So this is a fixed configuration. You should think of it as a regularized delta function, and it looks like this. And there's some
impurities located at the same place.
impurity is alpha of t, and you can see that it couples to psi I only in this region around the origin, where f prime is non-zero. Yeah, that's the role that f prime is playing. Yeah, it's useful to regulate the delta function with some size r0, but r0 is going to be small in this. All right, so these psi i's are chiral fermions, and this is the dynamical degree of freedom. All right. Let me remind you that this couples very much like a gauge field. If this were really a dynamical gauge field in 1+1 dimensions, this theory wouldn't make any sense. This would be, again, an anomalous theory. It would be a chiral fermions coupled to a U1 gauge field. So you can see already it suggests it might be interesting. It's kind of flirting with danger. If this was a function that depended on x and t, and both were dynamical, it wouldn't make sense. But as it stands, this is fixed and this is dynamical, so maybe it does make sense. That's the hope. And in fact, we'll show that indeed it does. But it's on the borderline of something that you might be nervous about. Okay. Any questions about this?
So can I think of this alpha as kind of a theta angle on the defect? If I go to both of the variables, looks a bit like a theta angle.
No, this is going to turn into the twist operator.
Twist operator for the...
Yeah, but at the moment, you should just think it's a bunch of fermions moving in one direction, and at this point, there's a little rotor degree of freedom that's ticking over, and this is how they interact.
From the UV perspective, can I think of it as if I turn off the gauge field, I have some phase in the
I see. So, sorry, I misunderstood. If you look at a Toft-Polyakov monopole, it has 3 position collective coordinates, has a little internal rotor degree of freedom that if you spin it up, turns the monopole into a dion. That's alpha. Yeah.
If I try to make this as a boundary condition for the fermion, it would be a phase in the boundary.
That's sort of where we're going. No, it's dynamical. Yeah, it's dynamical.
And you used folding it and thinking this is a boundary condition?
Yes, absolutely. So it's you're sort of jumping ahead of me, but I guess it's obvious. We've unfolded so that it's just simpler to write this way. But if I was to fold this back, no. Joe wrote down the unfolded version. It's just easier to solve this than worry about folding. But what?
The Carty state for,
Yeah.
I was going to ask, if you folded, can you come up with the Carty state?
I'll get there, and ultimately it will give that. But I'll get there. Yeah. Okay. Other questions? All right. So we've got something very solid. We've got a Lagrangian. What should we do? First things, look at symmetries. And what have we got? Well, there's a simple one, which is there's an SUN, global symmetry, with the size in the fundamental. There's n of them. You can just rotate under an SUN. At first glance, it looks like there's a U1 symmetry. And that U1 symmetry just rotates the phase of the size. But this is something like a gauge field. And so you may not be surprised to hear that this U1 symmetry suffers an ABJ anomaly. It's a global symmetry that the classical theory that is not a symmetry of the quantum theory. So this is anomalous. And the anomaly equation, which we'll need in a bit, is, I think, familiar, but is this. J is the sum over, what's this? Okay, you can see that if this is like the gauge field, the x component of the gauge field, then this is like the field strength. That's where this comes from, alpha dot f prime, whereas here it's just alpha f prime. Okay, so there's a U1 symmetry that doesn't survive quantization, but there is another U1 symmetry which is non-anomalous. Oh, I see. Because it's J mu. It's because it's chiral. So if you like, it's D plus J minus, I think. But yeah, this is what J is in this context.
It's a defect symmetric, but there is some non-trivial correct on the defect, which is alpha, which is
That's the next symmetry. There's a. Let me write down the next symmetry, and then you can re-ask your question. Okay, so this one's anomalous. The good U1 is psi I goes to e to the I beta, and then there's an f of x up there, psi I, and the rotor gets shifted at the same time. And so f of x is the integral of f, and looks like this. So this is the good symmetry. It's the f of x there that looks unusual, but this stops the thing being anomalous. It also means that the fermions on the left have negative charge, and the fermions on the right have positive charge. So the things coming in have different charges from the things going out, which is where the essence of this monopole scattering problem is feeding in. All right, so the upshot is that this model of Joe's has incoming fermions, which under the SUN and U1 symmetry they're in the fundamental of SUN and up to a factor of 1/2, which is a little bit annoying. I'll say they have charge -1 coming in. And then there's a rotor degree of freedom. And then the outgoing fermions are also in the fundamental, but now with charge +1. This f of x being the thing that shifts the charges. People happy? So you can see again, it captures the spirit of the monopole scattering problem. As Paul said, if I was to fold it, it would be closer to the monopole problem. What comes in is different from what goes out in terms of the quantum numbers. You throw in something with these quantum numbers, you ask what could possibly come out the other side. we'll rule out that very shortly. Yes, that's the first guess, but I'll shortly rule that out. So just to reiterate, this does come from monopoles in 4 dimensions. In that context, this rotor degree of freedom, as I said already, is the dionic collective coordinate that a 't Hopf-Polyakov monopole carries. It's the thing that if you spin it up, carries electric charge. In fact, specifically, this comes from the problem of SU2 broken to U1 coupled to n vial fermions. If you just take that reduced to the S wave, you'll find and unfold, you'll find exactly Joe's model.
Does that mean that
Yes. Yeah. And alpha is exactly the electric charge. Alpha dot is the electric charge. Yeah. And just a comment in. There's some obvious generalizations of this where I throw in a bunch of rotors at different points, and moreover, I give fermions different charges to different rotors. One of those is I have 2 fermions, a single rotor, but I give the 2 fermions charges 1 and 2 rather than both 1. It turns out that when they have charge 1 and 2, this actually descends to the 3, 4, 5, 0 model. It's not immediately obvious. You have 2 fermions coming in here with charges 3 and 4, 2 coming out here with charges 5 and 0. So this is sort of a UV completion of many of these Cardi state problems that we were dealing with, including the 3, 4, 5, 0.
Anomaly cancellation condition, you see, just the Fermion put the rotor in, where you see the anomaly cancellation condition, the Q squared, the equation like before. Right here, the equation for the cancellation of the gauge anomaly was Q squared left plus Q squared right.
No, it just comes out automatically from
And
this.
you cannot couple to the rotor device.
No, it's a bit different. Any coupling to the rotor gives rise to. Can I just tell you afterwards? Yeah. All right. So what happens? There's a naive idea, which everybody has, including me. This is Andy's idea from 2 minutes ago, which is that you throw in this fermion, which has charge -1. It comes out with charge +1, but what it does is leave charge -2 on the rotor. So it just leaves the rotor spinning. It would be analogous to depositing charge on the boundary in the context of BCFT. So you might be nervous that it's not right. Moreover, you might be nervous because there's a gap to exciting a rotor. First excited state costs some energy, whereas these guys can come in arbitrarily low energy. So, there's reasons to be nervous. Nonetheless, it sort of seems like perhaps it could be possible. It could be that coupling these fermions to the rotor changes the dynamics of this sufficiently to bring the gap to 0. So I think it's an interesting idea. It's also wrong, and I'll show you why it's wrong. So the U1 charge is. There's a contribution from the rotor spinning, and then there's the contribution from the fermions. So this is the observation that the rotor carries charge, and therefore maybe the charge could just be deposited on the rotor. So perhaps n-1 comes out as n+1 plus -2 on the rotor. And to see that this isn't what happens, you just need to solve the quantum equations of motion of this system. And actually, it's quite cute what you get. So if you look at the rotor equation of how are you? Good to see you. If you look at the rotor equation of motion, it's I alpha double dot is minus okay, so this is the rotor equation of motion. and J is fixed by the anomaly equation. So what you do is you integrate the anomaly equation, you substitute back into this, and you get an equation just for the rotor. And it's something I've never seen before in a quantum field theory, although maybe others have. All right, so this is the equation of motion for the rotor. It tells you how the rotor accelerates given a current which is coming in and hitting the rotor at some time t. If you set this current to 0, so you're not throwing any more fermions in, then you can see immediately that whenever the rotor is spinning, it decelerates. This is like a friction term for the rotor. And so the rotor quickly grinds to 0. And what I find cute about this is I've never seen a friction term emerging from a quantum field theory before. You know, equations of motion in quantum field theory have to be Hamiltonian systems. And obviously friction terms are the ultimate in a non-Hamiltonian system. It's coming because there's an impurity coupled to an infinite number of other stuff. So it's sort of not surprising that things can drain out of the impurity. Nonetheless, the interpretation of an anomaly as a friction term is new to me, and I thought was worth highlighting. It made me smile when I realized this was what's going on. I gave you the Lagrangian on the previous board. So the original action is there. It's just if you focus just at the impurity, what's really going on is the energy is draining out into the fermions. But you can see explicitly now that the charge cannot be stored on the rotor. That if the rotor is charged, it quickly drains away and goes somewhere else. All right. Charge conservation is there. I gave you the Lagrangian, found the U1 charge. Everything is charged. It's just that it ain't staying in, dynamically it's not staying on the rotor. It's leaking out into fermions. Okay.
Defer the answer to this, to the question I made, unless it's something useful. But there's this whole story called dissipated quantum mechanics, where you mock up dissipation. The way you make a quantum field theory out of this is by adding an extra dimension.
That's right. Caldera-Leggett kind of things.
Yeah. Exactly.
Yeah.
So, and in fact, this is Kondo-esque. So doing here, the envelope Kondo. And so what exactly happens there is you're looking just for what's happening to a given spin.
Yes, of course. Yeah.
And to mock up the effect of dissipation, you add an extra degree of, and that's the back.
That's exactly right.
And that's how you get dissipation in the theory. So I think you've just reversed the order.
So all the ingredients are there. It's more that the dissipation is the anomaly in this case. That seems like a novelty.
That was really well.
So,
in those days, they didn't think about it.
No.
So I'm wondering now if you just
Maybe there's a
framed the whole that whole story.
there's a connection between dissipation and anomalies. It strikes me as that would be interesting if it was more general than just this. Yeah, you can see why it's not bad that it's non-Hamiltonian. You see where the energy is going. But. All right, so okay, our naive guess is wrong. It's not that the rotor is storing the charge. So what is happening? Well, so Joe looked at the obvious things. What happens if you look at 2-point functions? Let's just create one of these here and measure what you see here. So look at 2-point functions. And in Joe's paper, there's a lovely, very technical calculation that shows you how to compute these 2-point functions. And what you get, well, it depends where you put the two insertions. If you put the two insertions on the same side of the rotor, So here's the rotor, and you put them on the same side, you get exactly what you would expect, which is a free propagator for a chiral fermion. I can give you the expression for this if you like, but it's not that useful. But if you put them on opposite sides, so you create it one side of the rotor and measure it the other side, you get 0. And you have to get 0 because the quantum numbers are different for the two things. So symmetry conservation tells you have to get 0. In fact, what Joe showed is that if you create something on one side and then try to measure that to any combination of fermions measured on the other side, everything is 0. So it was just showing that this has the scattering paradox. You send something in, there's nothing at all that can come out the other side, even though it's a unitary, well-defined quantum field theory. This was where Joe left it. So Joe, smart as he was, I think was unable to solve this problem. He didn't say he was unable to solve it in the paper, he just kind of left it as this. But I think it's true to say he was unable to solve this problem. All right, so it's just the statement that nothing can come out. And that was the situation for 40 years until sometime towards the end of last year. And at the end of last year, there was a beautiful paper by Vasya Loladze, who's a postdoc in Oxford, and Takeya Kui, who's in Florida. So this is Loladze, Kui from 24. Loladze, Vasya was Takei's PhD student and then moved to Oxford. They're both particle phenomenologists. They were caring about Kallan-Rubikov effect and proton decays and things like this. They found what Joe couldn't. They found the solution to this, and then there's a follow-up paper with me from last month. All right, so what did they do? I was the referee for their first paper. I was the first referee said this is so trivial, we've got to reject it. And then somehow I was the second referee, and it is so trivial that it took me ages to realize they'd done something really impressive, because mathematically everything is completely obvious, but it was missed for 40 years. And so my only job as a referee was to think, did I know this before? Because somehow as soon as I read it, I thought, I must know this. But I did not know it. I genuinely think they did something fantastic. And something which is obvious, but also surprising. So what they did is the following. They define the non-local operator after the rotor, which is the fermion dressed with a rotor degree of freedom. And you can see it's non-local if this is space-time, and you want to insert the fermion at some point. What you have to do is go back in time, be a 45-degree line, to see where it interacted with the rotor, and then insert that value of the rotor there. Okay. It has to be this particular non-local operator. Can't do anything else. And what they then showed, well, firstly, this combined thing has quantum numbers n-1. It turns out that this had quantum number n+1, but because this gets shifted under this U1 symmetry, the whole thing, even though it's to the right of the rotor, has the same quantum numbers as the thing to the left of the rotor. So it has the quantum numbers of the ingoing fermion, but it's a non-local operator. And then they showed that even though it's a non-local operator, when you put it in correlation functions, it acts just like a local operator. Everything is this, there's no hint of that non-locality. And in particular, if you create a particle on the left, the thing that comes out on the right that has a free propagator isn't the obvious thing. It's this non-local operator that's there. So so this is the answer to the paradox in Joe's model. What goes in? Do I still have that? What goes in carries quantum numbers n-1. It interacts with the rotor. What goes out naively carries quantum numbers n+1. But in fact, what happens is this thing passes through the rotor, and just like in the boundary conditions from the Cardi states, what actually comes out is, in as we'll soon see, a twisted sector. But again, there's something coming out here which carries quantum numbers that you would not naively thought existed in the theory. If you just did perturbative Fock space calculation, you would look at local operators, but there's a non-local operator that really describes local excitations here.
Well, again, to further answer this question, we're going to get there. But we asked the question before, is there a detectable thing just in the impurity that this happened? Meaning,
I don't
you
think so.
measure it long before the particle hits, long after. No way to tell.
I don't think so.
this cross.
No. Not that I know of. Let me say that. In either case, BCFT case or this case, not that I know of. Yeah. In the paper last month, we made the connection with the BCFT situation much more direct. So this result, and it smells like the boundary conformal field theory result. You send something in, the same thing just passes through with the same quantum numbers, even though naively that thing shouldn't exist. And so what we showed, among many other things in the paper last month, is that this rotor operator is a twist operator in the theory. And we could show this for the rotor versions of the 3450 model, for this model. What it means is that you want to compute commutation relations of this twist operator. And we did this in the paper. And they're not quite commutation relations if you have a twist operator. It's this weird thing where it commutes beautifully, or it fails to commute depending on the spatial ordering of the twist operator. I also learned this from Cardi, that this is the way to think about twist operators in Lorentzian signature. Okay, so it has the, not sure what we called it, but almost commutation relations, half commutation relations of a twist operator. All right, so to, I guess to pick up on something Paul mentioned previously, that this is an unfolded situation. Things coming in, rotors, things coming out with different quantum numbers. Were I to fold it, which is fairly easy to do, things come in, they interact with rotors, and then they bounce back with different quantum numbers. That's a fully unitary sort of UV completion of the theory. As I flow to low energies, the low here is relative to the moment of inertia of the rotor degree of freedom. Those rotor interactions must be flowing to the Cardi states, simply because there's a unique Cardi state that preserves these particular symmetries. So this is a UV completion of the Cardi states. One thing that would be very nice that we failed to do was compute the Affleck-Ludwig central charge from this perspective. That somehow, it's a subtle thing, the Affleck-Ludwig central charge. It's not like there's an internal degree of freedom on the boundary, but nonetheless it's contributing to heat capacities. So somehow those rotor degrees of freedom must be capturing that. But No, the rotor is gapped. Yeah, yeah. Cardi state's not really gapless in the sense of having extra degrees of freedom, and that's what I'm saying. Those G you shouldn't think of as the dimension of a Hilbert space of the boundary. Something more subtle than that. Yeah.
But I guess for the fermion state, the G function is something like proportional to n. There is a formula, no? Like one fermion G function is 1.
No, not these Cardi states.
Yeah, something you can distinguish the ones which are drafting from the ones that
In general, you could consider Pythagorean triples. Two fermions going that way with charges A and B, two fermions going that way with charges 0 and C, where A squared plus B squared is C squared. The boundary central charge for that is the square root of C. So even with two fermions, you can have the central charge to be arbitrarily large if you sort of want to make the difference big. All of that can be captured by one of these rotors. So somehow, even though the rotor is gapped and there's just a unique state, it's complicated enough that it's contributing to this central charge in a way that I would like to understand better. Maybe. I'd very much like to understand that better.
Actually, I was going to re-ask Andy's question. So probably still understand this either. So a Cardi state preserves conformal invariance. I see that's what, so the full system is conformally invariant. When there's no scale in there, then. So what's this gap?
Oh, so the Joe's rotor model was stuff in the bulk plus integral of dt, moment of inertia, alpha dot squared. This is the only scale in the game.
Does the Cardi state depend on I at all?
No. So when you look at energies E much less than 1 over I, it must be that the rotor model flows to the Cardi state.
Oh, okay. So I think you probably said this before. So basically, we're never exciting we're ignoring. We can just neglect all the excited states of the rotor.
That might be too strong. Because if you could neglect it, nothing was going on. It was just a unique state, and what could it possibly do? So the rotor's playing a role. That's right. Yeah, but it's not spinning the rotor up. It's not giving it charge. It's not alpha dot. Yeah.
The second example the same as from the first?
It's exactly the same. Yeah. This is a UV completion of the first example. So there's a consistent story. The story is stuff comes out that carries different quantum numbers from what you would think. In the BCFT case, it's because it's got a twist operator. In the rotor, that twist operator becomes something much more tangible, much more physical. But the low energy dynamics is the same.
Looks very much like the pictures that people from CFTs draw. Not only have some line that goes through it, and after the line goes through it, it's connected to the.
It's exactly the same, yeah. But somehow my problem with this entire project is taking pictures and turning it into physics. Because here it's very much
this is the
tangible. Yeah. All right, so I think it's been surprising for me to learn this stuff. You quantize the degrees of freedom in a theory. If there's a monopole or a boundary present, that's not the only local degrees of freedom that you can have. Other things that carry other quantum numbers. In 2D, I think the story is there. Lifting it up to 4D, I still find confusing because the obvious thing is that there's an S wave that comes out in the twisted sector. But this is a problem in the standard model. And when you talk about the standard model, you should ask very obvious questions, like what if it's an Atlas detector right next to your monopole? What does it see? And it doesn't see S waves, it sees localized particle excitations. So is all this also true in 4 dimensions? Is it also true that if you scatter off a monopole, there's a doubling of the spectrum of the standard model, that you can find right-handed SU2 doublets, and that would be an astonishing statement. But that seems to be what it's hinting at. If it's true, what does it mean? What's the early universe cosmology of this? It's so important. It's not doubling the fields. Yeah, it's doubling the spectrum, not doubling the fields.
Which of these links requires the lattice?
None. Because it's chiral. So it's very hard to sort of make the first step.
Yeah, but you have similar properties.
No, we tried to put 3450 on the lattice. When we succeed on that project, we can then turn to this project. And actually, this was, you know, this paper by Juven and Yi Zhuang, where they claim to put 3450 on the lattice, doing DMRG, but they do it with boundary conditions. So my first question was, how on earth did you get the boundary state, the Cardi state on the lattice? And of course, the answer is they didn't, which is one of several reasons why I'm not sure the numerics in that paper is right. That's right. There you can do it. Yeah, there's no problem. It would be interesting to try and put the Cardi state there. You're going to struggle because the whole point is that they have a lattice and they have a dual lattice, and there's some things living on lattice links and some things living on dual lattice links. And when you put a boundary, that's no longer so clean. You could do a zigzaggy one. It could be really nice to see if those lattice models naturally could admit a boundary. Yeah.
Well, yeah, so can I ask, like, okay, because this looks very much like taking the condo problem, but taking then the spin to be very large. So then the quantum purity basically becomes a problem. At least I think.
Do you know there's a simpler analogy, the two-channel condo problem,
Yeah,
the one that Goldhaber-Gordon actually cooked up in the lab in Stanford. This has this issue. If you think about let me see, it's two channels, but the spin comes for free, right? So really it's 4 Weyl fermions that come in. And the boundary condition you put there, it's a paper by Ludwig and Maldacena on this, turns there's an SO8 triality. So something comes in the vector of SO8 and comes out in one of the spinor representations so it comes out in a twisted sector. And Ludwig and Maldacena stressed this in that context. Now that's actually been built in the lab.
Maybe not the experiment you described, but yeah.
Oh, is it?
No.
No.
You can't do the scattering.
But all they see is, you know, VI curves, but in principle, what's coming out is in the twisted sector.
Scattering experiment. The observed transport stuff.
Yeah.
But no, but I mean even literally that your model could be obtained by just taking this infinite spin limit, so it basically becomes a class exactly your model. Well, or that's the question. Is that obviously wrong, or is this very possibly one could get that?
You want and I'm worried about the.
There's no results. It's you know you take SUN take some multi-channel zone and then literally just take this boundary spin to be very very large. I mean, people stuff this ages ago, and in some cases you find it. So I mean maybe there's something. See, the point is in that world they don't talk in this anomaly language. Doesn't mean it's not there.
Yeah.
And then the second thing, point is if that's correct, then it's easy. Then we know how to define this model.
Okay, that would be lovely.
So that, but that's then the interesting question: is there something fundamentally different about this particular model versus just taking some limit of these others?
Okay, I don't know. Sounds interesting.
Correct to say that double the number of states at the CFT, so the state operator corresponds with telling me I've doubled the number of operators, but my new ones are in some place topologically, so they don't change the central charge.
Yeah, but so you have to do the state operator correspondence for something that's not quite a local operator in the CFT language because it's a twist operator. Okay, so there's a story there, but I'm not quite sure how it goes through. But
The state operator is still okay, but then the central charge doesn't get changed.
what was the first statement? Central charge doesn't get changed.
The operator is still, but the central charge doesn't get doubled.
Yeah, but I think it's because these new operators are not quite local operators, so there's a slight change to the state operator map that others will know more than me.
How do you tell whether a particle is in a non-twisted sector or a twisted sector? Can you see the non-locality in some way?
How do we usually think about twist operators? We talk about Euclidean correlation functions and braiding one thing around another. It's very hard to do that experiment in the world. So, what's happening in Lorentzian signature is that something's coming, something's bouncing back. You might hope there's a branch cut, and you might hope you could do some kind of Aronoff-Bohm-like thing where you move through the branch cut, but the thing's going out at the speed of light. So it becomes very hard to see what kind of experiment would go through the branch cut and then come back round. So the answer is no. I did spend some time thinking and did not come up with a good answer to that. This is the closest I've got, is these commutation relations. It's quite abstract, but it is in Lorentzian signature, not Euclidean. Yeah, we do these same things, and you get a 5 instead of an n. Yeah.
What would I measure on the right to see that the object has the charge? Because locally I just see that.
You mean to make sure that all the charge is localized here rather than some of it there?
Okay, I want to measure something. Like you're telling me there's a surprising new excitation on the right, which has a charge with the charge of the left, but I can find it on the right.
Yes.
Can I do a measurement on the right and actually see here like charge n plus 1 on the left and minus 1 on the right? So can I actually see, and can I measure like a shot noise or something? There's some
Oh no, I think it's clearer than that. You just commute it with the charge operator. You'll see. You really want the current operator because it's some localized charge.
If I calculate the commutator of a local current, this is not a local object.
Yeah, we failed to do it, I have to confess. We did try. What I can say is the following, that the whole operator has this charge. And what I showed earlier in the talk is that any charge that's localized at the origin quickly decays exponentially. Where else is it? Everything's right moving. There's only right moving particles. Can't go to the left. But it would be nice to do a more direct calculation and show explicitly that the charge is localized here.
You're telling me the difference is like n plus 1 and n minus 1, the charge is sort of associated with your rotor is like 2.
Yeah.
Doesn't have to kind of wait till it has like multiple of like. And how can charge 2 possibly come out, right?
No, and it was never excited in the first place. It was always here. No, I believe that's not. It's certainly not true in the BCFT story. In the BCFT story, everything is here.
It's like the charge that's supposed to be different. It's just it's right moving from him on the right.
No. It sees the wrong charge.
No, I think there is a subtlety, but
How can the local operator see the rotor? I mean, it's sort of in the picture you're drawing, there seems to be like charge n minus 1 is associated with the permanent charge 2.
This one here? No, all the charge lives coming out. Yeah. It's exactly that, yeah. The obvious thing is you do bosonization. When you do bosonization, these things coming out are vertex operators that look like they're poorly quantized. E to the I5, but they don't have the right periodicity. No, because they're poorly quantized, so they're still not quite local objects.
But this order, there's always like some
true? Is that not just it's not a quirk of the Ising model?
Just think of it as rewriting in a basis, but you found that you could write down a theory just to be minus one. You know, the wrong
Mhm.
perfectly. But what happens, the boundary then couples this sector, then, if you wish, sector 1 to sector 2. And I mean, the central charge, you have to be careful when saying what the central charge is, because always you're again talking about sectors and things like that, and even how you're defining the central charge. So you're not adding any degree. I mean, so the point is, if you're living in a universe with just one free particle,
Yes.
you know, what does it mean to say the central charge, right? Because if you compute it using, say, the ground state energy, then you don't get whatever the central charge is, because there's an excited state.
Wait, I'm confused. Central charge is not a property of the state. It doesn't matter what's excited in your system. It's counting the number of degrees of freedom.
It depends on how you define it. There's lots. It's a very. Let's talk about this. But the point is, when you talk about different sectors, you're talking about added degrees of freedom. And what you're saying in the point is, when you make this statement, like in your original, oh, well, there's only 3, 4s, and 5s. That's right. You're imposing a particular boundary condition, which is saying, well, you know, there's none of this crap. But on the other hand, if I send one of the 3s off and it comes back, it's a different sector, and that's there, and that would affect the number of degrees of freedom.
No, but I'm not. The 3450 has, without weird boundaries, has central charge 1. Is that right? No, 2. Central charge 2. Thank you. Okay. When I put the boundary, the central charge is not 4 in the bulk. It's still 2 in the bulk.
Well, it depends on how you're doing it.
Let me say it maybe a little differently. It might be a bit wishy-washy what I'm saying. I think these extra degrees of freedom are extra degrees of freedom, but it's a tensor sum in the Hilbert space, not a tensor product.
Yeah, but that's the meaning of different sectors. The old quantum filtering language, super selection sectors. But what's the best?
But tensor product is what gives more central charge.
I mean, it's akin, actually, Frank's comment. So it's akin to an Ising model. You can look at things in the field theory. You can look at different bases, but so you can in the lattice. So yeah, you don't.
Lattice would make it clearer.
By saying, well, I can look at the just in terms of order fields or distance.
Ah, good.
I can look at it in terms of the fermions, and these things are basically the analog of the Ising fermions. And what you're saying is something very interesting, is that, but in a scattering experiment, I can do something very funny, which is connect the 2 sectors. But then when you talk about the central charge, I think you can say what's the underlying field theory and what's its central charge, and that's fine. That's not going to change no matter what crap you do. But then if you're going to define it in real life, you have to be a little bit.
All I really want to do is stress this was not a vector-like theory in disguise.
Yeah, no.
That was all the comments about central charge were just to rule out that possibility. That's not what's happening.
You can have both. They're different sectors. Sorry, I'll stop.
Maybe you can compute this the defect vector, you know, you just take the entanglement entropy with the defect inserted that you can try to project on.
Oh, that would be lovely. In the rotor model. Yeah, that would be great.
Yeah, that's not but react. That's my question. There there's some way to detect the string.
Yeah, the defect entropy should detect
exactly.
this twisted degrees of freedom, but people didn't really do this.
Wait, but this is calculating G.
No. So there are 2 things. So G is the partition function. You don't do that.
Yes.
Defect entropy is like you put the defect, you cut your system into 2 trace out alpha, and that scales logarithmic.
I see, and that's state dependent
Yeah,
now.
And then you can also try to do some symmetry resolution. You try to project on representation the symmetry, and that I don't know.
But it means that having the twist line or not having the twist line or the analog in the rotor model, you'll get different answers in those 2 cases. Is that?
I believe